In this video, we'll be looking at how to calculate the effective resistance of series and parallel circuits. In our last video, we deduced that for a series circuit, the effective resistance, which we can also call the total resistance, is the sum of the resistance of all the participating loads. While for a parallel circuit, the effective resistance, which you can also call the total resistance, is the inverse of the sum of the inverse of all the participating resistances. Now let's consider some simple circuits. For example, if we have a circuit in this form, we have this one to be 5 ohms resistor and this to be 5 ohms resistor. As you can see, this is a series circuit. If you don't know how to identify your series or parallel circuit, you can visit my last video. A link to that video is produced at the end of this video, or you can check the link that is displayed at the top of your screen right now. That will lead you to my last video on the basics of series and parallel circuits. So for this circuit, this is a simple series circuit, and for a series circuit, the total resistance, which is the effective resistance, is the sum of the participating resistances. So that means the effective resistance of this circuit is going to be 5 ohms plus 5 ohms, and that is going to give us a 10 ohms resistor. If we have another circuit in this format, we have another resistor in parallel with the first resistor. Let's say this is a 10 ohms resistor and this is another 10 ohms resistor. From our visual inspection, we can easily know that this is a parallel circuit, and to find the effective resistance of a parallel circuit, we have 1 over 10 over 1 over 10 raised to the power of minus 1. The purpose of this video is to learn how to calculate the effective resistance, and so we will not be going through the complexities of simplifying our fractions. So in that wise, let me pull up my calculator and let's get the value of this simple mathematical expression. So from here we can see that the effective resistance is equal to 5 ohms. If we have another circuit like this, let's say we have a resistor here, 2 resistors in parallel, and we have another resistor here. So let's say this is a 5 ohms resistor, this is 6 ohms, this is 6 ohms, and this is 4 ohms resistor. Now this is a typical example of a series parallel circuit. To simplify this circuit to find the effective resistance, what we first do is we first find the effective resistance of these 2 parallel resistors, and to find that we have 1 over 6 plus 1 over 6 raised to the power of minus 1. If you calculate this, you are going to have a 3 ohms value. So that means we can easily replace these 2 resistors with a 3 ohms resistor. So by redrawing, we have this to be the 5 ohms resistor. This one has a resultant resistor of 3 ohms, and this is going to be our 4 ohms resistor. Now these have formed a series circuit with 3 resistors. So and to find the effective resistance of this, we are going to have 5 plus 3 plus 4. This is going to give us 7, and this is going to total to a 12 ohms resistor. Therefore, the effective resistance of this circuit is a 12 ohms resistance. Now let's consider this kind of circuit. And let's call this 5 ohms. This is going to be 10 ohms and this will be 10 ohms. So we want to find the effective resistance of this circuit. This circuit may look some kind of complex, but to solve this kind of circuit, it is advisable you redraw your circuit, and in your redrawing, you restrict the layout of your resistors to both either horizontal or vertical positions. Now, if you want to redraw it, is more so advisable you label the joints for easy identification. So we are going to label these joints A. This one doesn't need labels, since these two resistors are just in series. So we can label this joint B. This joint is also not needful. These two resistors are in series. Now we have two named joints A and B. In redrawing our circuit, if we consider these two resistors, these two 10 ohms resistors, they are in series. So we are going to restrict their position to a vertical position. So we have two 10 ohms resistor in series, 10 ohms. This is point A, since we have them to be of the same values. You can say this is point A and this is point B. We have the first 10 ohms to be this and the second 10 ohms to be this. Now, between point A and point B, there is this 20 ohms resistor in parallel with these two. So between this is point A, we have a 20 ohms resistor in parallel with them. So this is the 20 ohms resistor. And between point A and B, we have these two 5 ohms resistor also. So this is still point A. This is a common terminal, it is the same. So we have two 5 ohms resistor. We have the first 5 and we also have the second 5. So this is the 5 ohms. This is also 5 ohms. So by our redrawing, we can see that this seemingly complex circuit has been withdrawn and it is now in a more simpler form. And by our visual inspection, we can see that these two resistors are in series. So the effective resistance of this branch is going to be the sum of these two 10 ohms resistor. So that means between this point A and B, we have effective resistance to be 10 plus 10, which is going to give us a 20 ohms resistor. In that wise, we can easily replace this with a 20 ohms resistor. So we can replace both of them with a 20 ohms resistor. This is going to be 20 ohms. Now, we can see that these 20 ohms and these 20 ohms resistors, they are in parallel. That means to get their effective value, we are going to have 1 over 20 for the first and 1 over 20 for the second, raised to the power of minus 1. If you calculate this value, this is going to give you a 10 ohms value. Let's test that out with a calculator. So we have 1 over 20 plus 1 over 20. As you can see, their effective value is 10 ohms. So that means we can replace these two with a 10 ohms resistor. So this is still at point A and this is point B. So we are replacing them with a 10 ohms resistor, since that is the absolute value of this. These two 5 ohms resistor, they are in series, so their effective resistance is going to be 5 plus 5, which will give us 10 ohms. That's why we can also replace this branch with a single 10 ohms resistor. So we can replace this with a single 10 ohms resistor. Now we have two 10 ohms resistors in parallel. So that to get the effective value, we are going to have 1/10 plus 1/10 raised to the power of -1. And if you find the value of this, if you find the resultant value, you are going to have 5 ohms. That means the effective resistance of this circuit, we can simply replace all of these complex circuits with just a single 5 ohms resistor. Let's consider another example that may look a little bit complex. We have a circuit like this. We have another resistor here, another resistor here, a resistor here, and a resistor here. We have another one going back. So let's make this 4 ohms. Let's make this 8 ohms. Let's make this 20 ohms. Let's make this 20 ohms. And let's make this 40 ohms. This should be 10 ohms. And this also 10 ohms. Now, if we have a circuit like this, how do we find the effective resistance of this circuit? As I've said earlier, it is more advisable to redraw circuit like this. Let's name this point A. Let's call this point B. All of these, they are connected to the same point B. Let's name this C. This, we don't need to name this terminals. This is just in series with this. So let's call this D. And let's call this E. Now to redraw our circuit, these two resistors, they are in series between points C and D. So we have both of them 20 and 20. This is the first 20, this is the second 20 ohms, the first 20 ohms. This is point C and this is point D. Now between point C and D, there is this 4 ohms resistor in parallel with this 220 ohms resistor. So that means we have the 40 ohms resistor here. This is going to be 40 ohms. And also between point C and B, there is this 10 ohms resistor. So let's have our 10 ohms resistor here. This is the 10 ohms and this is point B. Between point B and D, we have another 10 ohms resistor. This is point B and this is point D. We have this 10 ohms resistor. So we have 10 ohms between B and D. All of this is still corresponding to our point D. So we have this to be 10. Now between point B and A, we have 4 ohms. We have 4 ohms. This will be our point A. And between D and E, we have 8 ohms. So this is going to be point E. And this is 8 ohms. Now, we can see that this seemingly complex circuit has been simplified to this circuit. It is still the same. This is still 220 ohms. The 40 in parallel with them. This 10 between C and B. This 10 between B and D. 8 ohms between D and E, and 4 ohms between B and E. Now, considering this circuit, these two 20 ohms resistors are in series. So that means the effective resistance of this branch is going to be 20 ohms plus 20 ohms. And that is going to give us 40. In that wise, we can simply replace these two resistors with a single 40 ohms resistor. Now, these two 40 ohms resistors are in parallel. So to get the effective resistance of these two resistors in parallel, we have 1/40 plus 1/40 raised to the power of -1. So we can see that we have 20 So that means this is going to give us 20 ohms. So we replace this with a 20 ohms resistor. Now look at this. We have this 20 in series with this 10. So to get the effective resistance, we are going to have 20 plus 10 ohms. And that is going to give us 30 ohms resistor. We replace it with a 30 ohms resistor. This 30 is in parallel with this 10. So to get the effective resistance, we are going to have 1 over 10 plus 1 over 30 raised to the power of minus 1. This gives us 7.5 ohms. That means we can replace these two with a 7.5 ohms resistor. This will give us 7.5 ohms. Now, these three resistors are now in series. So the total resistance of this circuit is going to be 4 plus 7.5 plus 8 ohms. And that is going to give us 12, and this is going to give us total value of 19.5 ohms. Therefore, the effective resistance of this circuit is just a single 19.5 ohms resistor. And last example for this video, let's have a circuit like this. We have one here, another one here, one here, one here, another one here. Let's have one like this, and we have another one here and another one here. So let's say this is 5 ohms, this is 5 ohms, this is 10 ohms, this is 15 ohms, 20, 10, 30, 6, 8. As I said, it is advisable to withdraw this kind of circuit, and before you withdraw, you label the joints for easy identification while you withdraw. Name this C. Let's name this D. This point C. D. We name this E, and we name this F. Withdrawing, we have these two 5 ohms in series, so we can have them like this, both of them in series, 5 and 5. This is point C and this is point D. So we have C and we have D. We also have this 10 ohms resistor between point C and D. So this is C and this is D. So this 10 ohms resistor is this. Also, between point C and B, we have 15. So this is B, and this is the 15 ohms resistor. 15 ohms resistor. Now between point B and D, we have this 20. We have a 20 ohms between B and D. This is going to be 20. Now between D and E, we have 10. This is point D. So we have a 10 ohms resistor. This is going to be 10, and this is going to be point E. Between point B and E, we have 30 ohms resistor. This is point B, and between B and E, we have a 30 ohms resistor. This is going to be 30. This is point B and this is point E, the 30 ohms resistor. Now between B and A we have an 8 ohms. This is A. And between points E and F we have 6 ohms. So this is going to be point F and this is 6. Now this circuit is equally the same as this circuit. To easily calculate the effective resistance, these two 5 ohms resistors are in series. That means their total value is going to be 10, because 5 plus 5 is going to be 10 ohms. This is another 10 ohms resistor. Now this 10 and 10 they are in parallel, so their effective value is going to be 1 over 10 plus 1 over 10 raised to the power of minus 1, and that is going to give us 5 ohms. If you calculate that, you are going to have 5 ohms. So we can simply replace this with a 5 ohms resistor. Is going to be our 5 ohms. Now this 15 ohms is in series with this 5 ohms. So that means the total value is going to be 15 plus 5, and that's going to give us 20 ohms. That wise we can simply replace these two with a single 20 ohms resistor. Don't forget this is 20. And we are replacing those two resistors with a single 20 ohms resistor. As we can see, this 20 is now in parallel with this 20, so we are going to have 1 over 20 plus 1 over 20 to the power of minus 1, and if you calculate this, you are going to have 10. So we can simply replace these two resistors with a single 10 ohms resistor. We can replace it with a single 10 ohms resistor. This is the 10 ohms resistor. Now this 10 is in series with this 10. So that means their total value is going to be 10 plus 10, which is going to give us 20 ohms. So we can also replace these two resistors with a single 20 ohms resistor. So we have, is going to be is going to be 20 ohms. Now this 20 ohms is in parallel with this 30 ohms. So to get the effective resistance, we are going to have 1 over 30 plus 1 over 20 raised to the power of minus 1. So to calculate that, let's reach out to our calculator. So we have 12 ohms there. So these two resistors can simply be replaced with a 12 ohms resistor. This is 12 ohms. Now these three resistors are now in series, so their total resistance is going to be 8 plus 12 plus 6. This is going to give us 18, and this is going to give us 26 ohms. Therefore, the effective resistance of this circuit is just a single 26 ohms resistor. As you can see, it is very easy to simplify series and parallel circuits. Don't forget to subscribe to this channel. I'll see you in my next video.